We're now going to use the second derivative test for the critical points of our second example. Just a reminder that our function was x cubed plus 3xy plus y cubed. We took the partial with respect to x, said, hey, it's always defined, so we set it equal to 0. We took the partial with respect to y. We said, hey, it's always defined, so I set that equal to 0. And when we solved the equation, we wound up with two critical points, 0, 0, and -1, -1, but we don't know whether we have maxes or mins or neither. So we're going to do the second derivative test. So we need the four second derivatives. So fxx here is going to be 6x. fxy here, fxy is going to be 3. fyx is going to be 3, and usually those are the same. And fyy is going to be 6y. So we can write down our formula for D. For me, it's usually easiest to leave the variables in until I actually have to plug in the point. So this is going to be the determinant 6x, 3, 6y, like that. Now let's go do the second derivative test. Second derivative test says make sure you have a critical point. Create your little determinant D. When I plug in D of 0, 0 here, that's 0 for x and 0 for y. What I'm going to get is 0, 3, 3, 0. When I take the determinant of that, I get -9, which is less than 0. And according to the second derivative test, that tells us that P is a saddle point. The next one we need to do, just to figure out what we have, is -1, -1. We evaluate our determinant at -1, -1. And I'm going to get, let's see here, -6, 3, and 3 minus 6. That determinant is going to be 36 minus 9, which is equal to 27, which is bigger than 0. Remember what the second derivative test says. It says if you create this determinant and you get something positive, then two things can happen. It either has to be a local max or it has to be a local min. And it tells us what we're supposed to do is look at, either value works, but let's just look at that number right there. What is that number right there? We see that fxx there equals 6, which is negative. And what does that tell us? That tells us, remember what fxx in general tells us. It says you take a section and it tells you the concavity. Well, this tells us when we take a chop at x equals -1, we get something that's concave down. Well, if we know we're either at a local max or a local min, and the section is concave down, we're sitting at our section looks at a point like that. That's going to tell us the Q is local max. Ta-da!